Hi, I'm Mike Delmonaco. I'm a software engineer at Amazon Web Services, and I went to Northeastern University where I learned about Racket before the curriculum change. These days, I have a hobby interest in programming languages, and I do a little bit of programming language research with Michael Ballantyne, helping him make syntax spec, which is something that I use in this talk. So today, I'm going to tell you about a little language that I made, which allows you to perform deep immutable updates using patterns like match. So here's a sneak peek of the language. Let's say you have a list of 4 elements. My language update allows you to match on it like match with patterns, and then you can actually set bang the pattern variables, and it gives you the update as if it was mutation, but it doesn't actually do any mutation. And just an overview of how this talk is structured. First, we're going to walk through discovering what lenses are, which are the abstraction that powers this DSL. And that's a thing from Haskell, but don't worry, there's no monads in this talk. Next, I'm going to give an overview of the language, how it works, why it's useful, and then we're going to walk through the implementation. So before I get started, let's define some data types that we're going to use as a running example. So let's say you have a posin, which, as we all know, is a point in 2D space with an x and a y coordinate. We have a rectangle, which has a top left position and a width and a height. And let's say you want to move a rectangle to the right. So you would just do a struct copy. You have this helper function called posin move to right, which is another struct copy. And you get the value of the field, do something to it, and then you use struct copy to update the original value. And if you want to move it to the left, it's pretty much the same thing, except you use a different helper function. So we're good how to design program students. These functions are almost identical. Let's circle the difference and then make an abstraction. So our abstraction is called rect modify top left. You take in a rectangle and a function which describes what you want to do to the top left, which is a function on posins. And then you just perform that struct copy operation. And we can do the same thing for a posin by making posin modify x. And so in both of these examples, we have a target, which is the overall structure that we're working with, and then we have a focus, which is a piece of that structure that we want to do something to. And so for rect modify top left, the target is a rectangle, and the focus is its top left position. And for posin modify x, the target is a posin, and the focus is its x coordinate. So here is the data definition for modifiers. There's a target type and a focus type. We take in a target, a function on the focus, and we return a new version of the target without doing any mutation. So rect modify top left is a modifier rect posin, and posin modify x is a modifier posin number. Putting this to use and inlining the helper function, we get this, which doesn't really look much better than a struct copy in a struct copy, but this is a modify inside of a modify. So why don't we just compose these two things together and make rect modify x? So here's what that would look like in terms of our diagrams. We end up with a modifier that targets a rectangle and focuses on its x value. So it's kind of like we took the diagram for the posin and just plopped it right into the orange part of this diagram, and that's exactly what composition does. It allows us to chain these modifiers together so we can do deep immutable updates inside of a structure. And the implementation for modifier compose is exactly what you think it would be. It's just a modify in a modify, except now we take in 2 arbitrary modifiers, and the target and focus types just have to line up the right way. And so now we get this nice compact implementation where we have a separation of where we want to perform a modification and what we want to do at that point. And in practice, it's often useful to package the getter and the modifier together, and we call that thing a lens. So this is sort of like a first-class immutable dot top left that you would see in a more traditional imperative language, except since it's first class, we could pass it around and compose it, and it's immutable, so no spooky action at a distance. Here's a data type for lenses. We again have a target and a focus type, and the getter just takes in the target and returns the value of the focus. And just like modifiers, we can compose lenses together. For the getter, you just do a get and a get. And we can have other types of lenses, not just struct lenses. So here we have the car lens, which targets a cons pair and focuses on its car. And we can also do something like a hash key lens, which is a function that takes in a key and then returns a lens that targets a hash map and focuses on the value at that key. And just to get some sensible behavior on lenses, we can specify some laws, because we're going to end up making some weird lenses soon. So we want to just define some laws for sanity checks so that lenses don't behave weirdly. Wait, that's wrong. There we go. So first of all, you can get a setter from a modifier by just supplying a procedure that returns a constant value. So if you set a new focus for the target, and then you get that using the getter, you should get that focus that you just put in. And if you get the focus and then you set the new focus to that value, it shouldn't change the target. And lastly, if you set the new focus twice, it should be the same as if you just set it to the new value once. So these are just sanity checks to make sure that lenses have sensible behavior.
Is it equal or E?
It's equal, huh? Like, I guess, probably equal, huh? Maybe not eq, because things might end up getting, because you're going to do a struct copy, so equal. It's not going to be eq. And so far we have seen struct fields, we have seen car, but what about list elements? So if we want to move a rectangle to the right, if we want to move a list of rectangles to the right, we use map. And this actually looks just like the modifies that we did. So map is kind of acting like list modify rectangle, since we're talking about a list of rectangles. So can we do list rectangles lens? Well, here's what that would look like in terms of our diagrams, and we see that it's weird. So a list can have 0 elements in it, in which case there is no focus. It can have 1, in which case there is 1 value for the focus. Or it can have a bunch of things, and there are multiple foci. And so this is very different from the examples we've seen before, because the number of foci that we might be working with is potentially 0 or more. And notice that the target type is list of rectangle and the focus type is just rectangle, because we have a procedure that takes in a rectangle and returns a rectangle. Okay? So for our if we look at the signatures for the lens that this would be, we have a getter which takes in a list of rectangles and returns a single rectangle, which is in general not possible, because if you have the empty list, you don't have a rectangle to return. So clearly, lenses are not the right abstraction for this, because we cannot implement a getter, because there may not be a value for the focus. So we make a new data type called a traversal, which has a fold instead of a get, where you fold over all of the foci. In practice, you don't end up using the folder very often, but we just have it in there because it's the closest thing we have to a getter. And by the way, the umbrella term for lenses and traversals and all these things is optics, because there's like focusing and stuff. And so here's the implementation of list traversal. The folder is foldel, and the modifier is map. And just like lenses, we can compose traversals by doing a fold and a fold and a modify and a modify. And so if we compose list traversal with itself, we get a traversal that targets a list of lists, and it focuses on all of the elements of all of the sublists. I don't know why you'd want to do that, but you can. And so let's think about the relationship between lenses and traversals. Lenses have 1 focus. They're good for stuff like struct fields. You have a getter and a modifier. Traversals, you have 0 or more foci. You can do a fold because you can't do a get. And it's good for focusing on collections. So lenses turn out to be a special case of traversals. So all lenses are traversals, because there's 1 focus is a special case of 0 or more foci. And because lenses are traversals, you can cast a lens into a traversal and then compose it with a traversal. And I made a thing called optic compose, which handles all the casting and selecting the appropriate composition operator. So here we can clearly see we're composing the list traversal with the rect top left lens and posit X lens. And that gives us a traversal that targets a list of rectangles and focuses on the X values of those rectangles. So this is what you would use if you want to move a list of rectangles to the right. And traversals on their own, you usually wouldn't use list traversal by itself, because you could just use map, and that's easy, straightforward, everyone's used to it. But where the real power comes from is when you compose traversals with other optics, because it allows you to kind of map a lens over a collection, which is really useful. Now, so far we've talked about lenses, which are good for struct fields, and traversals, which are good for collections. Let's look at another example. So let's say you want to do symbol upcase. Racket has string upcase, but the standard library does not have symbol upcase. So instead, we can convert the symbol to a string, do string upcase, and then convert it back. Because string is more convenient for this, so we have to do this back and forth conversion. And another example of equivalent data, let's say we define bounding boxes, which are kind of like a rectangle, except we have a top left position and a bottom right position instead of having a width and height. So these two things are equivalent. They're just different ways of representing the idea of a rectangle. Now, let's try moving a bounding box to the right. So we're all excited about lenses, right? Let's try to use lenses for this problem. So naively, what you might do is you would take the bounds top left lens, which focuses on that top left position, and then you'd compose that with positive x lens, and you would try to increment the x value. But since you have a separate top left and bottom right, that ends up just moving the top left and not the bottom right, so you end up squishing the rectangle. So you would need to move both positions in order to move the rectangle without changing its shape. And so clearly rectangles are more convenient here because you only have to move one thing. So we can convert the bounding box to a rectangle, move it to the right, and then convert back. Now, in both of these examples, we have this operation that is more convenient on a different representation of the data that we're working with. So we do this back and forth conversion. And again, we're good how to design program students. Let's make an abstraction for this. So we will call that abstraction an isomorphism, which is Greek for same shape. And we just package the forward conversion and the backward conversion together. And you'll notice that I made target focus diagrams, even though this feels very different from the stuff we've been looking at so far. So we have lenses and traversals, which work with little pieces of a data structure that we want to operate on. But this is very different because the target is some data, and the focus, if you want to call it that, is just a different version of that data. So we're not focusing on a little piece of this structure inside of it, we're focusing on another version of it or another representation of it. But I would argue that this actually does behave like the things we've been working with, because we can define isomodify, which handles the back and forth conversion, and this looks just like traversal modify or lens modify. And so we have the isomorphism here, which has this cute double arrow notation. And then we just supply the target and the function that we want to apply to it. And that works just like our other optics that we've been seeing. So this is a more abstract, weird version of lenses and traversals, but it follows the same sort of pattern. And so here's the data definition. We just store the forward and the backward conversions, and they ought to be inverses of each other so things work right. Now, let's think about how this fits into the hierarchy of optics. So lenses have one focus, traversals have 0 or more foci. Isomorphisms have one focus that's a different representation of the target. And we have forward, which is kind of like a lens getter, because forward gets the value of the focus, which is the more convenient representation. But weirdly, we also have backward, which lenses don't have any analog of, because here, given the string, we can recover the symbol. But if I just gave you the x value of a posin, you can't get the posin back because there's not enough information. But since these two representations are equivalent in the case of an isomorphism, we can actually recover the target from the focus. So clearly isomorphisms are a special case of lenses. And so all isomorphisms are lenses, which means they're also traversals. Okay? And because of that, we can compose them with the other types of optics. So here we compose the bounds rect isomorphism with the rect top left lens and the positive x lens. And this is pretty weird. It gives us an optic, in this case it's a lens, that targets a bounding box and focuses on the x value of the rectangle that it is equivalent to. And so, importantly, if we modify on this optic, we move the whole rectangle as one, not just moving only the top left and not the top right. And the power of isomorphisms, again, comes from, well, they're useful on their own just for this backward-forward conversion automation, but in the context of other optics, the power comes from being able to talk about rectangle lenses when you are working with a bounding box. So it's kind of like a translation adapter, which is really cool to be able to use. And taking this one step further, we can compose that whole thing with list traversal. So now we get a list of, it targets a list of bounding boxes, and it focuses on the x values of the rectangles that those bounding boxes are equivalent to. So if you wanted to move a list of bounding boxes to the right, this is the optic that you would use. Now, let's review. Isomorphisms are good for when you have equivalent data representations, and lenses are good for fields, and traversals are good for collections, but where the real power comes from is when you compose all of these things together. And the really important thing about lenses and why I think they're actually useful, or in optics in general, is they allow you to separate the where from the what. So if you're moving a list of bounding boxes to the right, you have this optic which tells you, here is exactly the part of the structure I want to be manipulating, and then here is what I do to, here is what I want to do to it. And you have this very rich language for specifying where, if you would even call that where. And it's composable, it's reusable, and then it allows you to separate the where from the what, so everything is nicely decoupled. So now let's talk about update. So the inspiration for this, how I came up with this language is, I was looking at match and I said, what if you could set bang the pattern variables and that actually updated the value of the target that you're matching on? And you can't do that with match, and to see why, let's look at how match actually works. So this is a crude oversimplification of how match gets translated to racket, but roughly what happens when you match on a posin pattern like this is you end up saying let x be posin x of p, and then you get the body. So if you set bang x, you're just mutating the reference to x. You're not changing anything about the posin, because there is no connection to where the x came from. You only get the value. And furthermore, if you have a nested pattern, you end up doing a temporary variable, and then you do a field-to-field access. And so there is no connection all the way back up to the posin. There's no way for it to know how x would transform and how that would affect the target value. So how could we possibly get immutable updates like the way we want? I'll give you a hint. It has something to do with what I've been talking about for the past 20 minutes. We bind variables to lenses instead of the values. So here, if we have posin x, we would bind x to struct lens posin x, which is a macro that makes posin x lens. And so now we have access to the information of how to get the value, but also how to transform it. And so for nested patterns, we again use temporary variables, and then we use lens composition instead of field-to-field access. And for set bang, we translate that to lens set, which is implemented in terms of lens modify. And for variable references, like here, we translate that to lens get. And it's not just lenses either. So if you have a list pattern with ellipses, so you're matching on a list of positions and you want to manipulate all of the x values of those posins, you get this x, which ends up being bound to list traversal composed with posin x lens, and then you can do modify bang to update all of those x values at once. And so before we get into the implementation, there are a few tricky bits that we need to think about. We have this special variable behavior. We want to customize the behavior of set bang and references so it does something different than as if you just bound it to a value. We have struct name patterns, like we have the posin pattern, so we have to have a special case for that. We want to duplicate pattern variable check, so if you have like x and x in a pattern, we don't want to allow that because what should that do? And we also, it would be convenient if we could allow users to make macros for new patterns, and also us as the implementers, so we can have syntactic sugar, so we can have patterns in terms of other patterns. And we also have modify bang, which is kind of like set bang, but it's not a built-in thing. So these last two in particular are tricky, because for macros, you basically need to make your own expander, and for modify bang, you need to do some fancy transformer stuff. Luckily, there is a tool called syntax spec, which helps us take care of all of these things. So I'm going to briefly give an overview of syntax spec. Michael will talk about it a lot more tomorrow. But basically what you do is declaratively describe the core grammar of your language, binding rules, macro extensibility, all that stuff. And you implement a compiler which translates your language to Racket, which is just one big macro, basically. And then you get all of these nice things for free, basically. So our implementation is going to be split up into two main components: the expander, which is written in syntax spec, and the compiler, which is a macro that translates patterns into optics and lets, and then it also transforms those set bangs and variable usages in the body. So here's the grammar for patterns. We have the wildcard pattern, the variable pattern, struct names like the posin, cons, list, and list with ellipses. But as it turns out, some patterns are equivalent to simpler ones, like this list pattern is just a bunch of cons patterns. So we can use syntactic sugar there. And even patterns that aren't equivalent to each other compile to very similar code. So if we have the cons pattern here, this is just going to be let A be car lens, and we have this posin pattern, it's just going to be let X be struct lens posin X. So we can make a general optic pattern that just takes in the optic that we're going to end up binding a variable to, and then the sub pattern to match on. And the compilation is very simple. We just bind, in the case of a pattern variable, we just bind the optic to the pattern variable. And also, when you have multiple subpatterns, like if you had cons AB, that's going to end up being multiple lets. So we can make an AND pattern that captures this idea of having multiple patterns matching on the same target.
Yeah.
And so our core grammar for patterns actually ends up being very small. We have wildcard, variable, optic, and AND. And that's really nice because our compiler is only going to have to worry about those 4 things, and then we could just have a bunch of syntactic sugar on top of that. So here's the actual syntax spec implementation of our expander. I've blurred out a bunch of things, and we'll fill it in as we go. So here's the way you write down this grammar. We have the wildcard. We have pattern variables. We have the optic pattern, which has a racket expression and a pattern, which is what we're defining here. And then we also have the AND2 pattern. We'll make an AND macro that is variadic. Next, we have binding rules. I won't go too into detail about these, but what we care about is that these binding rules make it so all of the variables from the patterns end up getting exported and bound. And this also leads to a duplicate pattern variable check. So if we have duplicate pattern variables, this will cause an error. Next, we declare macro extensibility. So we have an extension class called pattern macro that declares a new type of macro. And we allow patterns to be extended by pattern macros. Next, we define a binding space, which allows us to make a pattern called cons without shadowing Racket's built-in cons. And we have to have a special case for struct fields or for struct patterns, because we have a special form for optic, we have a special form for AND2, we're going to make a macro for stuff like cons, but you can't make a macro for every possible struct name. So we have to have this special case which uses syntax classes to detect a struct name, and then it rewrites that into struct star, which is a pattern macro that will end up expanding to uses of optic and AND. Okay, and this is what cons looks like. You do define DSL syntax, which is from syntax spec. We're declaring that this pattern macro is called cons, and it is a pattern macro so that it can be used in patterns. And this is just a regular old Racket syntax rules, except it's written in terms of patterns instead of regular Racket code. And here is the implementation of list. The empty list gets translated to wildcard. If we have an ellipsized list, this just turns into list traversal. And if you have a non-ellipsized list, it just gets translated into cons. Now, if you've ever implemented match with ellipsized list patterns, it is a huge pain. You have to do this backtracking, you have to get all of the free variables of the ellipsized subpattern, you have to do this loopy thing where you do the submatches, and then you collect all those values into a list. It's so much work. But with this, you just say list traversal, and the optics do all the heavy lifting. When I saw how easy that was when I was making this, I was so happy that I didn't have to do that. And that's honestly like one of the reasons I'm doing this talk, just to talk about how insanely convenient that is that you don't have to do that. And so next step is to define the entry point. This is the barrier between Racket and our language. We do this by declaring a host interface, and we're going to call it update. The first argument is a Racket expression for the target. And then we have a single clause, which is the pattern and then the body. And this binding rule is basically just saying that all the things that are declared in the pattern are in scope for the body. So all the pattern variables are in scope for the Racket body. Next is our compiler. So first we bind target to a temporary variable to avoid duplicate evaluation. And then we call bind optics, which is our main compiler that's going to translate all of our patterns into optics and lets. And that is just a macro that we'll define in a second. And then we also set up a parameter called current update target. So when we do something like a set bang, it's going to mutate that parameter to keep track of the current version of the target as we perform immutable updates on it. So the only thing we're mutating is this parameter. Okay. So here is the pattern compiler. Underscore does nothing. It just gives you the body. Variables bind an optic. The optic pattern uses a temporary variable in optic composition. And for AND, we just do bind optics inside of bind optics, which is going to lead to nested lets. Next, we have to take care of the body compiler, which is the second big component. I hesitate to call this a compiler because the body is just regular racket code. We're just customizing specific behavior of certain parts of it. So we have to establish the runtime context, which we already did back in the update host interface. We have to do custom variable behavior for references and set bang, and then we have to do special stuff for modified bang. So we already handled the runtime context, setting up that parameter. Next, we have to do custom behavior for set bang and references. So references, we want to translate that to lens get, and then set bang, we want to translate that to lens set. And normally in Racket, there's this thing called variable-like transformers. So you could say, instead of let x be posin x lens, you would have to say let syntax x bound to make variable-like transformer, and then some stuff about how you want the references and set bangs to behave. And your compiler would have to do that. So your compiler has to worry about all these syntax bindings and transformer stuff. Luckily in syntax spec, it's a little bit easier. We declared a binding class called pattern var, which is what we referred to before in the grammar. And we declare a reference compiler. So reference compilers control the behavior of DSL-bound variables when used in Racket expressions that they're in scope for. And we use make variable-like reference compiler, which is sort of similar to make variable-like transformer. And we pass it the behavior for references and set bang. So references, we want to translate to lens get. And for the target, we use that parameter, current update target. And then for set bang, we want to use lens set on the current update target, and then mutate that parameter, and finally return the new value of that parameter. So our compiler, remember, it literally outputs let x be posin x lens, and then this is going to end up translating the Racket body so that it will use that lens that x is bound to as lens set. So our compiler doesn't need to worry about that though, which is nice. We have a separation of how the Racket body transforms from the semantics of patterns. And before we talk about modify bang, let's do something simpler. So let's say we want to give an optic form in the body where I don't want the car of this pair, which is what you would get if you just said A. I want the optic that A refers to. And normally this would be impossible because if you have A, it's too late. You already have the car. You already have the value, and you can't recover the optic from it. So we need to do something. So optic needs to do something to prevent that from happening. And so syntaxspec gives us another little trick. We can make a new host interface called optic, which takes in a pattern variable and just returns the raw reference. And because this is a host interface and not just regular Racket code, this will prevent the reference compiler from transforming that reference to the lens get behavior. And remember, since our pattern compiler bound x to the lens, we will actually get the lens here. And we can implement modify bang in terms of this optic form. And it's just like what we do for set bang. We use traversal modify, current update target, mutate, and then return the new value. So that is it. We have just implemented our update language in terms of lenses and using syntax spec. And before I go, I want to thank a few people. I want to thank Michael Ballantyne for helping me with this talk and helping me improve the update language to be more convenient to use, and also for letting me help him make syntax spec, which has been a lot of fun. I'd like to thank the authors of the Haskell Lens library, because that was a big inspiration for the Lens library that I ended up making. And of course, the Racket community for making all these wonderful tools that I get to use, and for organizing this great event. And if you are interested, the library and DSL are available in the Ocular Pat-Down package.
All right, thank you, Mike. We got time for some questions.
Hello, I'm Jacqueline, and I made 3 lens libraries in Bracket.
I've seen some of those.
Yeah. And I just want you to know that I like yours better.
Thank you.
Have you done anything with prisms yet? Or
Yes,
have you just not?
library does have prisms, which are like an isomorphism that is only possibly in one direction. So for example, numbers and strings have a prism because you can kind of do string to number and number to string, but if the string doesn't represent a number, it doesn't work in that direction. So it's kind of like a partial isomorphism.
Yeah, I like to think of it as kind of like a cast, just
Yeah.
casting from one type to another, and sometimes it works, and sometimes it doesn't. That's all.
When you were working with this where did you find syntax spec wasn't as nice as you wanted?
Wasn't as nice as I wanted.
If you don't want to say it while he's here, you can tell me later.
I didn't run into any limitations with syntax spec as far as I remember. I think in general with match, there is something that we're still trying to figure out how we want to do it for OR, right? Like, because OR, that's the only place where you want to allow duplicate pattern variables and you want to make sure they're the same. There's nothing built in for the binding rules to support that right now, so that is one limitation. But OR would be weird for this anyway, so I didn't really care that much. I just didn't do it. But yeah, that is one limitation. Originally, I had references just give you the optic, and then I made a get form that calls lens get, because I didn't realize that there was a way for you to just have the custom reference behavior and the set bang behavior and optic. Those are the 3 things I wanted to do. And so I didn't realize that you can have an optic form after the fact when you have the reference behavior just do the lens get for you. Michael suggested using another host interface. I didn't come up with that. So there are some tricks in syntax spec that you have to know that are something that you wouldn't intuitively come up with on your own maybe. So, but stuff like that could be solved with documentation potentially.
Yeah, so you mentioned the Haskell lens library. And of course, I've written some Haskell, and like modern Haskell, lenses are all over the place. Like
Yeah.
they use lenses everywhere. Have you shown this to any Haskell programmers, and what do they think?
No.
I think they might be jealous because I don't think you can do that in Haskell.
Do what in Haskell?
The
macro.
macro.
Well, what's nice about this is you don't have to even know what a lens is to use the update thing. I just talked about it because it's cool.
Yeah.
Like this, I tried to completely abstract lenses away. It leaks a little bit because you have to know the distinction between a traversal and a lens kind of, but in the documentation, I don't really talk about that. I just say if there are multiple values for a multi-valued pattern variable, you have to use traversal stuff instead of lens stuff. But for the most part, the abstraction of lenses does not leak out in the pattern language, which is cool. And yeah, Haskellers would be jealous about the pattern thing. Oh, one thing I forgot to mention. I find patterns are much more convenient to think about than optic compositions, because you say, oh yeah, rect top left lens, pos and X lens, but what's way more intuitive is the visual language of patterns, where you could just say where it is in terms of what the structure looks like. So that's another advantage of that. But yeah, haven't shown this to any Haskell people. I'm sure they would scoff at the implementation because it doesn't use profunctors or whatever stuff they use.
It's okay, I'll show them.
Well, I had to implement composition manually in terms of the structs, and I had to do manual function composition, but they just use regular function composition for lenses because it's like some crazy, like const functor or something.
Yeah, it uses the type class system as well. Yeah.
Oh, first, that's a. Okay.
Thanks, this looks great. I'm wondering about how update works. Like if I match on 10 pieces and I use setbang to update only one of them, does the compiler know, oh, I don't have to rebuild this part of the thing? Like if it's a tree of things and I only modify this part or another part even conditionally?
Are you
It
talking
sounds
about a deep
hard.
modification or like a wide modification?
Uh,
Or both?
a selective wide modification, right? I modify this
Yeah.
part and I don't modify this other part.
So what will end up happening is, let's say you have a field you have a struct with like 100 fields or something, and you modify just one of them. That will just get translated to a struct copy on that one field.
Right. So there's nothing you can do in the case of a struct, I guess. But I'm imagining if I did enough matching to do a small tree of structs, and I only modified the left-hand pieces and not the right-hand pieces.
It depends on the implementation of the underlying lens, but for anything sensible, I would assume that you would end up just like reusing the reference to the other side of the tree that's not modified, and it wouldn't even look at that.
But with the, I'm not even sure what the right piece of it. I guess the lens it would have to notice that all the things that it would want to reconstruct are the same.
Well, like let's say you have a binary tree, you have like a left child lens and a right child lens.
Yeah.
The pattern variable is going to end up being bound to something that gets composed with the left child lens, and then you're going to do lens modify on that, which is going to completely ignore the right child. So it depends on the implementation of the lens for the tree, but any sensible implementation would hopefully just ignore anything that doesn't need to be changed and copy the reference.
Maybe I should have been wondering about a different thing, which is if I match on 5 variables and I have 5 settings, is that going to do 5 struct copies? Or?
Yeah.
Ah, okay.
Yeah.
Then I see how the trade-off works. Thanks.
Yeah, there's no like intelligent optimization for anything like that.
But okay, you're in syntax spec. Can you make that?
I could, yeah.
Okay, thanks.
Well, I have to think about that. Because that involves runtime stuff too. And like parallel set bangs, there is something called a multi-lens that you could do, but that doesn't really fall into the pattern of lenses in my library, so it might be possible.
Yeah, I mean, it doesn't always work, but an optimization would recognize case work.
Yeah, I would have to add runtime support for that optimization, but it's possible.
But
Any more questions? All right, then I think let's thank our speaker one more time.